Picture a table. On one side, a steaming cup of freshly brewed tea. On the other, a glass of water, packed with ice. Our common sense tells us exactly how to label these objects. The tea has a high temperature, or a high degree of hotness. The ice water has a low temperature, or coldness. We can perceive this difference instantly just by reaching out and touching them. But human skin is a remarkably unreliable thermometer. Our basic sense of touch is simply too limited to be useful for precise scientific measurement. Saying something is hot or cold is really just making a relative comparison, exactly like calling someone tall or short. It categorizes the objects, but it tells us absolutely nothing about the underlying physical mechanics at play inside those glasses. If we leave both of these drinks sitting on that table on a warm summer afternoon, we know from experience exactly what happens next. The ice water slowly warms up, and the hot tea gradually cools down. Why do two objects in completely opposite thermal states move toward the exact same physical destination? The answer lies in the air around them. Right now, the temperature of both the tea and the ice water is different from their surrounding medium, the ambient air of the room. That gap in temperature acts as an invisible engine. Objects do not possess a permanent grip on their thermal state. Instead, they are constantly forced to interact with their environment to resolve that difference. To understand that interaction, we need to look at how physicists define these concepts, separating our everyday idea of hotness into two distinct terms: temperature and heat. Temperature is a relative measure indicating the current physical condition of an object. In the International System of Units, this condition is officially measured in Kelvin, a scale that starts at absolute zero, though we commonly use degrees Celsius in daily life. Heat is an entirely separate concept. Heat is the actual form of energy that transfers between a system and its surroundings. Because it is a form of energy, it is measured in joules, the standard metric unit used to quantify work or energy transfer. This gives us a strict rule for the physics happening on our table. Temperature is the static condition that currently exists, while heat is the active transfer of energy that occurs precisely because of that condition. This diagram shows energy flowing around our ice-cold water. Animated arrows move from the surrounding space into the glass. Because the room's air is warmer than the ice, the environment acts as the source, forcing heat energy into the colder liquid system. Now, this diagram shows the exact opposite process happening to our hot tea. Arrows flow out of the liquid into the environment. Holding a higher temperature than the room, the tea becomes the active source, continuously bleeding heat energy outward into the surrounding air. Whether an object feels freezing cold or burning hot to our touch, the underlying physical law driving its behavior is identical. Heat energy always flows from the medium with the higher temperature to the medium with the lower temperature. If we fast forward a few hours, that invisible engine finally runs out of fuel. Both the water and the tea stabilize, matching the ambient temperature of the room perfectly. We can observe the physical evidence of this stabilization right on the table. The steam has completely disappeared from the teacup, and condensation has stopped forming on the outside of the water glass. This diagram shows what happens to the energy flow at the finish line. As the temperature difference between the liquids and the room shrinks to zero, the heat transfer slows down and stops completely. Physicists call this final state thermal equilibrium. Thermal equilibrium is the exact point where a system and its surroundings share the identical temperature, effectively neutralizing all heat transfer between them. This brings us back to a major misconception. Our intuition tells us that a hot object contains a specific fixed volume of heat locked inside of it. But once thermal equilibrium is achieved on our table, the concept of heat vanishes from the interaction. There is no more heat to be found here. By strict scientific definition, heat only exists as energy in transit between two or more systems. Heat is not a property you can measure in isolation, nor is it a physical substance an object can hoard. It is an active, temporary event born entirely from a difference in temperature, and it ceases to exist the exact moment that balance is achieved.